Welcome you all for today's session. Today we'll see unsymmetrical bending of beams. So this topic comes under the Module 1 of Advanced Strength of Material course. We will see what is meaning for unsymmetrical bending, how the unsymmetrical bending happens, and also the unsymmetrical bending, how it differs from the normal bending. So all those things we'll discuss in detail in this today's lectures. I hope you all enjoy this session. Now we see the recapitulation related to the today's topic, the theory of simple bending and bending equation. In theory of simple bending, when beam is subjected to a loading system or force couple acting on a plane passing through the axis, then beam deforms. In simple terms, this axial deformation is called as a bending of beams. The beam undergoes deformations due to shear force and bending moment. When the deformation is more simultaneously, the shear force and bending moment also will be the maximum. The normal stress due to bending are called as a fluxural stress. So this is some theory related to the simple bending. So based on that simple bending theory, the equation is derived is called as a bending equations, which is called as m by I equal to sigma divided by y, E equal to E divided by R. The bending equations, uh, where m is the bending moment. So we know that a bending moment is nothing but force into perpendicular distance. The unit for bending moment is Newton meter. Then I is the moment of inertia of the cross section of the beam. So the moment of inertia, which will be varies depending upon the cross section of the beam. The cross section may be circular cross section, square cross section, rectangle cross section, or channel sections. So based on the moment of inertia of the cross section, the moment of inertia will be value will be changing. So the unit for moment of inertia is millimeter square. Then sigma is the bending stress which is induced during the deformations. The unit for bending stress is Newton per meter square, where y is the nothing but the distance of neutral axis from the external fiber of the beam, that is a y. So unit for y is meter. Then E is the Young's modulus of the material of the beam. So based on the material of the beam, Young's modulus also will be changing. E is the Young's modulus of the material of the beam. Unit for Young's modulus is Newton per meter square, where capital letter R indicates that is the radius of curvature of the beam. Unit of radius of curvature is meter. So when beam undergoes deformations, it will make some curvature. This curve is having one arc. The distance between the center point of the arc and the radius of curvature, which is nothing but the radius of curvature. So this equation is called as a bending equation. M by I equal to sigma divided by y equal to E divided by R. So this equation can be used to find out the bending stress or any other parameters which is not known. So by substituting the values, we can find out the other values. For example, in this equation, if you know the x modulus, radius of curvature, and y, then if substitute the values and we can find out the bending stress. In another way, so if we know the bending moment, moment of inertia, and y value, then in that case also we can find out bending stress. So this is about theory of simple bending and the bending equation. The objectives of today's lecture is unsymmetrical bending of beams of symmetrical section, unsymmetrical bending of beams of unsymmetrical section. During this unsymmetrical bending in symmetrical section as well as in unsymmetrical section, when beams undergoes unsymmetrical bending, so what will be the value of stresses induced on the beam and corresponding deflection induced on the beam? So this is the objectives which will be going through in detail in this lecture. So now we'll see what is meaning for symmetrical bending. While using the well-known simple flexure formula m by I equal to f divided by, it is assumed that the neutral axis of the cross section of the beam is perpendicular to the plane of loading. This condition implies that the plane of loading or plane of bending is coincide with or parallel to the plane containing a principal central axis of inertia of the cross section of the beam. So this is the meaning for the symmetrical bending. So in simple way, if you want to understand symmetrical bending means, just if you consider a beam AB, so it's subjected to bending. So because of some bending moment, the beam A is undergoing bending action. So then with respect to vertical axis of the beam, if you see either side, the deformation is similar on either side, then that this type of bending is called as a symmetrical bending. Now we'll see what is the meaning for unsymmetrical bending. The plane of loading or the bending does not lie in or parallel to a plane that contains the principal central axis of the cross section. The bending is called unsymmetrical bending. In case of unsymmetrical bending, the direction of neutral axis is not perpendicular to the plane of loading. So this is the case we will see in the unsymmetrical bending. So suppose if you see the figure, so this is a cross section of the beam is a C channel cross section. One end of the beam is fixed, other end is free. So the free end is subjected to the load P. When load is acting on the free end of the beam, the C channel cross section is subjected to bend as well as twist these other directions. So if you see that bending, nature of bending with respect to vertical axis, which is passing through the center of the cross section, if you see either side, the deformation will be not be a similar form. So it is not a similar form and also not symmetric deformation on either side of the vertical axis of the cross section of the beam. So this type of bending is called as unsymmetrical bending of beam. The reason for unsymmetrical bending: the section is symmetrical but load is inclined to both the principal axis. So that is one of the case for unsymmetrical bending. The section considered is symmetrical but the load line is inclined to both the principal axis. Symmetrical cross section of the beam, for example, the rectangular cross section, circular cross section, I section, all those comes under the symmetrical cross section. The load is inclined to both the principal axis, then the bending is called as a unsymmetrical bending. Second case where the unsymmetrical bending occurs is when the section itself unsymmetrical, load line is along any of the centroidal axis, then in that case also unsymmetrical bending occurs. For example, the cross sections like angle section or channel section where the unsymmetrical bending occurs. These are the two main cases of unsymmetrical bending, so which occurs mainly due to either section is symmetrical with load is inclined to both the principal axis, or in another case is when section itself symmetrical and load is acting along the any of the central cases. Either up to one case is there, then the bending will be the unsymmetrical bending. We'll see the stresses due to unsymmetrical bending. Figure 1 shows the cross section of the beam under the action of bending moment M acting in the plane YY. Let G is the centroid of the cross section and XX and YY are the coordinate axes passing through G. Just we considered the one cross section of the beam of having this XX and YY centroidal axis. Then this cross section of the beam is subjected to bending moment M. So because of bending moment M, this the cross section of the beam is twisted to another axis that is called VV and UU principal axis, which makes an angle theta with respect to the x-axis. So this UU and VV is called as a principal axis. And if we take the components of moment, the bending moment, there are two components are there. One component is acting along the UU principal axis, that is m dash equal to m sine theta. Another component which is acting along VV principal axis is m double dash equal to m cos theta. Okay, we will see the moment m in the plane yy can be resolved into the components in the planes uu and vv as follows. That we know that moment in the plane uu principal axis m dash equal to m sin theta. Similarly, the moment in the plane vv axis m dash m double dash equal to m cos theta. The components m dash and m double dash have their axis along UU-VV axis respectively. The resultant bending stress at the point PUV is given by sigma B equal to m dash U divided by IVV plus m double dash V divided by IUU. So where m dash is, we know that is a component of bending moment along UU axis. M double dash is the component of bending moment along VV axis, where U is the location of the um, point with respect to VV axis, and V is the distance between the point P from the UU axis. IVV is the moment of inertia with respect to VV principal axis. IUU is the moment of inertia with respect to UU principal axis. By substituting the value of m dash and m double dash in this equation, then finally sigma b will be resulted as m sine theta u divided by IVV plus m cos theta b divided by IUU. The final equation of bending stress becomes sigma b equal to m into b cos theta divided by IUU plus u sin theta divided by IVV. At any point, the nature of sigma b will depend upon the quadrant in which it lies. In other words, the sign of u and v will have to be taken into account while determining the resultant bending stress. So the nature of the resultant bending stress may be positive or negative or value, which depends upon the quadrant in which the point is selected. So based on that, the bending stress value may change. It may be a negative value or positive value. The equation of the neutral axis Na can be found out by finding the locus of the points on which the resultant stress is 0. So thus the points lying on neutral axis will satisfy the conditions that sigma b equal to 0. So we know that at the neutral axis stress is equal to 0. So in case of normal bending, simple bending, so there will be a neutral plane will be there. So in the neutral plane the bending stress is 0. The portions above the neutral plane will be subjected to compressive nature, and the portions of the beam which is below the neutral plane which will be the tensile nature. So at the point of at the neutral plane axis, the bending stress equal to 0. So because of by substituting this condition sigma b equal to 0 in the bending equation, then it becomes m into v cos theta iuu plus u sin theta divided by IVV equal to 0. So this is the bending equation at the neutral axis. Once after substituting the bending equation equal to 0, so we will then the equation finally reduce to v equal to minus iuu divided by IVV into tan theta into u. So this is the equation of a straight line passing through the centroid G of the section and inclined at angle alpha with UU, where alpha can be determined by using this equation tan alpha equal to minus IUU divided by IVB into tan theta. So once if you find out the value for alpha, we can find out this equation of straight line passing through the centroid G, and which makes an angle alpha with respect to the UU axis. Important points in stresses due to unsymmetrical bending. The maximum stresses will occur at a point which is at greatest distance from the neutral axis. The second one is all the points of the section on one side of the neutral axis will carry the stresses of same nature, and on the other side of the axis of opposite nature. For example, if you consider the bending of beams, the beam is subjected to bending. So the center of the beam will have the neutral axis and neutral plane. The portions above the neutral plane, that is towards the bending, that portion will be subjected to compressive nature of stresses. Then some portion of the beam which is away from the neutral axis, that is outside outside portion will be subjected to tensile stresses. Third case is in the case where there is a direct stress in addition to the bending stress, the neutral axis will be straight line but not passing through centroid of the section. Next, we'll see the deflection of beams due to unsymmetrical bending. Figure 2 shows the transverse section of the beam with centroid G. Let x and y are the two rectangular coordinate axes, or otherwise called as a centroidal axis, x and y axis, and uu and vv are the principal axes inclined at angle theta to the xx xy set of coordinate axes. These are the u and vv are the principal axes. W is the load acting along the line YY of the section of the beam. So this is the cross section we have considered. So we are having x axis and y axis. Then the load will be acting along the y axis. Because of application of the load, the beam will be twisted to a new axis. That axis is called as a principal axis, UU axis and VV axis. When load is acting, then corresponding components also there. Components along the axis PV axis is called as M double dash, which will be equal to W cos theta. The component of load along the UU axis is equal to M dash, which will be equal to W sin theta. So where W sin theta is the component along UU principal axis and W is the cos theta is the component of load along VV principal axis. Let del U is the deflection caused by the component W sin theta along the line GU for its bending about VV axis. And del V is the deflection caused by the component W cos theta along the line GV due to bending along UU axis. Thus, depending upon the end condition of the beam, the value of del U and del V are given by del U equal to K into W sin theta L cube divided by E IVV, and del V equal to K into W cos cube theta into L3 divided by E into LUU. So where K is a constant depending upon the end condition of the beam, and W is the load acting on the YY axis, and theta is the angle of inclination of principal axis UU with respect to XX axis, where L is the length of the beam, E is the Young's modulus of material of the beam, IVV is the moment of inertia of the cross section of the beam with respect to principal axis VV, and IUU is the moment of inertia of the cross section of the beam with respect to UU principal axis. So with these values, we can get the component of load del U and del V. So it's nothing but the deflection component del U and deflection component del V can be calculated by using the given formula. The total or resultant deflection del can be found out as follows. Del equal to square root of del U square plus del V square. So we already find out that value for del U and del V, which are the um, components of deflection del. So the substituting value of del U and del V in this equation, then finally the equation will be reduced to del equal to KWL cube divided by E square root of sin theta divided by IVV whole square cos theta divided by IUU whole square. The inclination beta of the deflection with the line GU is given by tan beta equal to del U divided by del V, which will be equal to IUU divided by IVV tan theta. The inclination of the deflection del value with respect to UU principal axis can be determined uh, by using this formula tan beta equal to del U divided by del V. The questions for today's session is, so what is meaning for unsymmetrical bending of beam. So we have seen that unsymmetrical bending of the beam which results due to the two cases. One cases when the load is acting on the symmetrical section which is inclined to any one of the principal axis. The cross section of the beam will be the symmetrical cross section, but the load acting on the beam is inclined to any one of the principal axis. This results in unsymmetrical bending. The second case is the cross section of the beam itself unsymmetrical, and then which is subjected to loading on any one of the principal axis. This case also results finally in the unsymmetrical bending of the beam. So these two cases results in unsymmetrical bending. Then we have seen uh, derivation for the stresses developed due to the unsymmetrical bending. So what are the steps are followed to derive the equation for the bending stress which is induced due to the unsymmetrical bending? And also that third question also we have seen that derive the equation for the deflection of the beam subjected to unsymmetrical bending. We have seen the derivation for deflection of the beam subjected to symmetrical bending. So these three questions we are covered in this today's lecture. Just you can go through it and you can familiar out these questions. So the reference book followed for this today's session, and that's Rajput RK, the Strength of Material Mechanics of Solid, Estend and Company Limited, New Delhi 2010. Then William A. Nash, The Theory and Problem of Strength of Materials, Sachin's Outline Series, Tata McGraw-Hill Publishing Company, year of publication 2007. Then third book is Punmia BC, Theory of Structures, Volume 1 and 2, Lakshmi Publishing Private Limited, New Delhi 2004 publications. These books are referred for preparing this PowerPoint preparation. I hope everyone understand the unsymmetrical bending of beams and their derivation for stresses developed due to unsymmetrical bending and deflection due to unsymmetrical bending. Thank you for watching. Thank you.